My pleasure to introduce Benjamin Schweinhart from the Ohio State University, and he will be speaking today on persistent homology and the upper box counting dimension. Thanks, Ben.
All right, thank you very much for the opportunity to speak. So, as Henry said, I'll be talking about persistent homology and the upper box dimension. Um, okay, and I seek to address two different questions, and it turns out that they end up being the same question in some sense. So the first question is, what is the relationship between fractal dimension and persistent homology? And this is a question that has been studied since the advent of the study of persistent homology. In fact, I believe the very first paper on persistent homology did some computations with fractals. I'll talk about that more later in the slides. And in particular, we seek to address whether the fractal dimension of a metric space can be computed in terms of its persistent homology. So we'll be looking at a particular notion of fractal dimension, the upper box dimension. I will define that later in the talk. And the idea is, to get an idea, we can look at this figure. So this is example of a self-similar fractal, Sierpinski triangle. And what you should see here is, as we take the epsilon neighborhoods of the Sierpinski triangle, we have homology classes that are born and die. And this is reflected in the persistent homology. And the idea with this very special case is that the set is self-similar, so the persistent homology should have should inherit this self-similarity property. And from that, we should be able to see the self-similarity dimension. Now, I should say the word fractal dimension does have the word fractal in it, but it's in fact defined for many different metric spaces under relatively weak hypotheses, and the metric space itself doesn't need to be self-similar. But this is just a good example to have in mind to get intuition for what's going on. Okay, so more on that later. And also, I wanted to mention a separate thread of motivation for this is, can classical results relating minimal spanning trees and fractal dimension be generalized? And we'll see that the persistent homology dimension I introduced in this talk is a direct generalization of a quantity that has long been studied for minimal spanning trees of points in Euclidean space and in more general metric spaces. So I'll say a little bit more about that later. First, just so we get on the same page, I assume everyone here knows persistent homology, but I just want to make sure we're using the same notation. So here we're going to be concentrating on the special case of the persistent homology of the epsilon neighborhood filtration of a subset of a metric space, such as is shown in this figure. So just to establish notation, the epsilon neighborhood of a subset of a metric space is the set of all points within distance epsilon from that subset. So in the picture, we have a few different epsilon neighborhoods of this modified Sierpinski triangle. And the basic idea here, and the idea of persistent homology, is to consider how the homology groups change with epsilon. Okay, so to establish notation, so as I said, the persistent homology will be the persistent homology of the epsilon neighborhood filtration. That is, it's this product of the homology group of x epsilon for all epsilon greater than 0, together with, I forgot an hi here, together with the inclusion map between the homology of x epsilon 1 and x epsilon 2, if epsilon 1 is less than or equal to epsilon 2. So this has the structure of a module, and we can apply the decomposition theorem under some mild hypotheses that are, I guess, always going to hold for the for this type of persistent homology, which will give us that the structure of the persistent homology has a canonical representation as a set of intervals. And as all of you know, each interval tracks a homology generator in the homology groups of x epsilon that is born at epsilon equals b, i.e. the first time this homology generator appears is in the homology of the b neighborhood of x and dies at the d neighborhood of x. So just to refer back to the figure, if we take a look at, I don't know, the big triangle in the center, that doesn't give a homology class until the very thickest epsilon neighborhood in the bottom right here, and that's when it's born. It's born at this time. I guess we have a formula for the birth time here in terms of a parameter used to make this triangle. Okay, and then later on at a time we don't see here, that will die. So if we take the persistent homology, we will get an interval that corresponds to this homology class that forms and dies as we increase the parameter epsilon. Okay, so I'm going through quickly because I'm assuming everyone here knows this. Okay, and we're just going to abuse notation and say that PHI of X is just the set of intervals in the canonical decomposition, and we're only going to be looking at bounded intervals. For a subset of Euclidean space, you could just take reduced homology and all the intervals will be bounded. But we can also define all the concepts here for more general metric spaces. Okay, and just a few remarks on this definition. PHI of X depends on the ambient metric space. You can define persistent homology in ways I'll say in a second. One of them where it doesn't depend on an ambient metric space. So the dimensions we're going to be I'll say a little bit about the RIPS complex later, but most of what I'm talking about today depends on an ambient space. And in most of my talk, that ambient space will be a Euclidean space. I'll get there later. So yeah, persistent homology depends on an ambient metric space. If X is a finite point set, then the persistent homology as I've defined it is the persistent homology of the check complex, which I assume all of you are familiar with. And also, in the special case of X being a subset of Euclidean space, this is also the persistent homology of the alpha complex, which is a filtration on the Delaunay triangulation. So I'll be using this fact later to prove upper bounds for the persistent homology dimension. Okay, and I just wanted to say that, as I mentioned before, there are other ways to define persistent homology. It's a much more general thing. This is just the special case of most interest to us. I'm also interested in taking the persistent homology of the RIPS complex of metric space. Here, you don't need an ambient metric space, and I'll say a little bit about that later. And a lot of results I have today will be stated for the check complex. The specific bounds, with one exception, will just be for the check complex, but most of the technical results I have can work equally well for the RIPS complex. They just depend on the stability of the bottleneck. So I'll say more about that later. Okay, so any questions about the setup, background? I assume we're all on the same page here. Okay. So I just like to review the motivation a little bit. So as I said before, this question of the relationship between fractal dimension and persistent homology, the observation that there should be a relationship here dates back to the advent of the study of persistent homology. To be specific, in the thesis of Vanessa Robbins, written in 2000, she studied the persistent Betti numbers of fractals. And using these persistent Betti numbers, she defined a dimensional quantity that measured how they scaled, how the Betti number of the epsilon neighborhood of a fractal scaled as epsilon goes to 0. I'm not going to go into the technical details. There's going to be a lot of technical stuff later, so I just want to give an overview. So she defined a dimensional quantity in terms of that, and compared computational estimates of it with known dimensions. She also proved some results for the H0 of disconnected sets, and I believe Hn-1 of some upper bounds for Hn-1 of subsets of n-dimensional Euclidean space. So this is the first, I believe, the first paper on persistent homology. Correct me if I'm wrong about that. But already it was seen that there's this interesting relationship between fractal dimension and persistent homology. Now, jumping ahead to 2012, my first paper with my PhD advisor, Bob McPherson, So we were unaware of the results of Robbins, and we proposed similar but not the same sort of fractal dimension based on persistent homology. Instead, we looked at the scaling of the size of intervals, persistent homology intervals, and we proposed a fractal dimension based on that in our paper in 2012, Measuring Shape with Topology. And in that paper, we computed estimates of this fractal dimension and for probability distributions of polymers, and we compared it with known and conjectured dimensional quantities. So this dimension actually is related to the dimension I'm going to propose today. The dimension I'm going to propose today is a little different. It actually gives an upper bound for the dimension I proposed in the earlier paper, and I can say a little bit about that at the end of the talk if people would like to see that. And I should mention...
Ben, quick question. So I've looked at Vanessa Robbins' thesis, but I'm not. I haven't read it all in full detail. Is her dimension defined mainly as epsilon's going to 0?
Yeah. It just looks at well, it's the thing is, for any fixed epsilon, you're going to have a finite Betty number. So basically, you look at the scaling as epsilon goes to 0. Of how fast does the persistent Betty number grow? Or how fast does the Betty number grow as epsilon goes to 0?
But persistence comes into her definition. It's not just Betty numbers.
It's just Betty numbers. This is
before
persistent, before any of the papers on the decomposition theorem or anything like that was written.
Right.
It just looks at Betty numbers. Yeah.
Great, thanks. Whereas your work with Bob is looking at the lengths of the intervals. So
yes, the lengths of the intervals. Yeah. Exactly. Thanks for clearing that up. Okay. Actually, your paper is what I'm going to say next. Is a paper that Henry wrote with several people at Colorado State University. They proposed an alternate definition of persistent homology dimension for measures. I'm not going to go into the details of what they did, but it's so the dimension I'm going to propose today is a generalization of a quantity defined for minimal spanning trees. What Henry proposed is a generalization of a different quantity for minimal spanning trees, a related quantity that's not the same. And their work is what, in their computations, what got me interested in this problem again, because the dimensions proposed by Robbins and then by McPherson and myself, they don't agree with classically defined fractal dimensions in general. And Henry did some computations and showed that this dimension agreed with some classically defined fractal dimensions for some specific examples. And now that got me thinking of whether I could prove some results, rigorous results relating fractal dimension and persistent homology. Okay. So then, as I said, the dimensional quantities proposed by Vanessa Robbins and then the different one proposed by McPherson and myself, they don't agree in general with any classically defined fractal dimensions, such as the Hausdorff dimension or the Box dimension. Instead, they measure the complexity of a shape. If I had a little more time, I could go into computations of the dimensions. And for this example of the Cantor set across the interval, these dimensions only see the Cantor set part of it. So if we take them, we'll get for both pH0 and pH1, the definition proposed by McPherson and myself will give the same answer as the Cantor set. Now, this is an interesting quantity because it says something about the complexity of the shape. Somehow crossing with the interval doesn't really increase the complexity of the shape, but it does increase the fractal dimension. So then the natural question is, can one define a persistent homology dimension for metric spaces that agrees with a classically defined fractal dimension under relatively weak hypotheses? And we're going to take the first step toward answering this question today. Okay. So just to get briefly to the second thread of motivation for the work that I'm presenting in this talk, it comes from the literature on minimal spanning trees. So if M is a metric space and we take a finite subset of it, we can look at the minimal spanning tree. That is the minimal spanning tree with the smallest length. So this can be given by Kruskal's algorithm. And we can define the alpha weight of the minimal spanning tree to be we take the sum of the lengths of the edges in the minimal spanning tree, and we take the each length to the alpha power. Okay, so cool facts about this is the tree produced by Kruskal's algorithm, it works for all alpha. It's minimal for any alpha. So it's just, you're given a finite point set, the tree, the minimal spanning tree is minimal for any alpha weight. So we should just take a second and think about this alpha weight a little more, because it will come into play a lot later. So just to reiterate, it is the sum over the lengths of the edges in the minimal spanning tree of the length of the edge to the power alpha. And I wanted to say, I don't have time to go through the whole literature here, but the properties of E alpha 0, this should be, the properties of this alpha weight for minimal spanning trees have long been of interest in Euclidean combinatorics, both for extremal and random point sets. And there's papers going back to the 40s that relate this quantity for Euclidean minimal spanning trees to the ambient dimension for extremal point sets. So there's a long literature on this. And so in 2005, so that work was for Euclidean minimal spanning trees, relating it to the dimension of the ambient space. So in 2005, Kozma, Lotker, and Stoop decided to ask whether these results could be generalized to spaces of arbitrary fractional dimension. And they proposed a minimal spanning tree dimension for a metric space. So in that 2005 paper, they proposed the minimal spanning tree dimension as the cutoff beta for which everything below that the minimal spanning tree dimension, if beta is less than the minimal spanning tree dimension, we can find point sets in our metric space whose beta weight is arbitrarily large. And if beta is above the cutoff, it's going to be uniformly bounded. Now, for example, if we're in a bounded subset of R2, our cutoff is going to be 2. So that means for a subset of R2, we can find point sets so that, let's say, the 1.5 weight of that point set becomes arbitrarily large, but we can't do that for anything greater than 2. Okay, so Kozma, Lotker, and Stoop defined this minimal spanning tree dimension of a metric space. And they proved this very general theorem, beautiful theorem, which is that if M is any metric space, no hypotheses at all, and dim box of M is the upper box dimension, which I'm going to define for you later, then the minimal spanning tree dimension equals the box dimension, i.e. we can see the box dimension by looking at extremal minimal spanning trees of our metric space. Okay, any questions about this definition? All right. So this pretty easily generalizes to higher dimensions using persistent homology, using key observation, which is that if we have a finite subset of a metric space, there is a bijection between the edges of the minimal spanning tree and the bounded pH 0 intervals. And this bijection takes an edge to an interval of half the length. Then we can see that we can rewrite this alpha weight of a minimal spanning tree in terms of the persistent homology of the finite point set. Instead of taking half the sum over the lengths of the edges of the minimal spanning tree to the alpha power, we can instead take the sum over the pH 0 intervals of the lengths of the intervals to the alpha power. Okay, and this works both for persistent homology as I defined it in terms of the check complex. This also works for the Riffs complex. In fact, this is an easy generalization of this concept of the alpha weight of a minimal spanning tree to just an arbitrary subset of a metric space. This definition works for any subset of a metric space. We can take the epsilon neighborhood filtration rather than just a finite point set where we have this minimal spanning tree. Okay? So, okay.
This is a very small, silly remark, but in the minimal spanning tree dimension, you had the one half out front.
Yeah.
Here, aren't the one halves being raised to the alphath power?
No, the 1/2 is hold on. Good point. You're right. I'll
It
have to
doesn't
think
really
about that
matter,
later.
I don't
I should have
think.
noticed that earlier.
Yeah,
Okay, thanks for pointing that out.
yeah.
Yeah. Yeah. Okay. Yeah, I'll have to think about that for a second later. Okay. So here we have okay, so this presents a way to obvious generalization, which is here we have the 0, we can just turn this to an I. And so we say that the alpha weight of the ith dimensional persistent homology of a subset of a metric space is the sum over all the bounded intervals in the ith dimensional persistent homology of the death minus birth to the alpha. Okay? And then we can define the persistent homology dimension. So then we look for the cutoff so that the beta weight of any subset, we could look at finite subsets, we could look at arbitrary subsets. Stability of the bottleneck distance says that this will be the same quantity. So we look at the cutoff for the beta for which anything less than that, we can find subsets where the beta weight is arbitrarily high. Anything greater than that, we can find subsets where the beta weight is the beta weight will always be uniformly bounded for any beta greater than the cutoff. So that's what the definition of the ith dimensional persistent homology dimension is. And we can also, as I said before, the constructions here work equally well for the Rips complex. I'll say a little bit about the results for that later. So we let denote with a wide tilde the Rips persistent homology dimension. And we have this result that we get all of these dimensions agreeing for I equals 0. So the question is, can we generalize this to can we generalize this result to higher dimensions? Okay. So then our main question, revised version of this, is remember that originally the main question is, can we define a persistent homology dimension that agrees with a classically defined fractal dimension in under relatively weak hypotheses? So here we've narrowed it down to two specific persistent homology dimensions, DMPHI and the Rips version. And so here we ask, are there hypotheses on a metric space M under which the persistent homology dimension equals the box dimension for I greater than 0? First thing I want to point out a couple things is we can't expect to have no hypotheses like we did for the minimal spanning tree dimension. The minimal spanning tree dimension, the result it holds for any metric space. But that is not true for higher dimensions. For example, if we just take a line in Euclidean space, then the ith dimensional persistent homology dimension equals 0 for I greater than 0, but the box dimension equals 1. Okay, so that says, oh, we can find things whose box dimension is higher than their persistent homology dimension. And also, if we look outside of Euclidean space, we can construct a metric space whose Rips persistent homology dimension exceeds the box dimension, which is why for the remainder of this paper, we're going to restrict attention to subsets of Euclidean space, because that gives some more regularity properties. If you're interested in this construction, it is in my preprint on the archive.
And Ben, is there a version of that construction that works for the check complex as well? Do you know?
Probably, but I have not worked it out for that. Yeah. Okay. So this is the main question. Are there hypotheses on a metric space under which the I-dimensional persistent homology dimension or the Rips version equals the box dimension? Okay. So our main result is, well, if X is a bounded subset of the plane, whose box dimension exceeds 1.5, then the one-dimensional persistent homology dimension equals the box dimension. And this may seem like fairly restrictive hypotheses, and I'm hoping to get stronger results in the future. But I just wanted to point out that this is quite a general result. There's many interesting subsets of the plane whose box dimension exceeds 1.5. Not only does this result apply to things like the Sierpinski triangle, but here we have a picture of I guess one of the components in a critical percolation. In the scaling limit, the components of critical percolation clusters, are going to have a box dimension that is greater than 1.5. And this was proven for percolation on the triangular lattice by Smirnov. So that means that this thing, which isn't a self-similar fractal in the discrete sense, this satisfies the hypotheses of the theorem. So here we're saying that we can see the fractal dimension of it in terms of the persistent homology. Okay. So we also have some more restricted results in general cases. Now, proving these results turns out to be quite difficult because it raises related questions in extremal combinatorics, which are quite hard to get a handle on. I'll talk about those later. So we have more general results that if X is a bounded subset of Rm and the box dimension is greater than m minus 1/2, then the pH1 dimension is between the box dimension and the dimension of the ambient space. Okay, let me see how much time I have left. Okay, and I just wanted to state a conjecture that more generally, we want to conjecture that if we look at a subset of Rm and I is between 0 and m, there is some constant gamma of I of m, so that any bounded subset of Rm whose box dimension exceeds this gamma satisfies the persistent homology dimension equals the box dimension. So our previous result, the main result we've proven, is for the case I equals 1 and m equals 2. And I have some other results on bounds for this. We'll talk about them later in the paper, where we don't get a direct comparison between the box dimension and the persistent homology dimension. Instead, we have a comparison between multiples of them. So I'll say more about that later.
And in your theorem in the planar case, and then your theorem in the Euclidean space of dimension m, here you're using gamma is equal to 1/2.
Here, gamma is 1.5. Gamma of Im is 1.5.
I see. Okay. And in I guess in the theorem in Euclidean space of dimension n, gamma is m minus 1/2.
Yeah, but this isn't proven. This is we only have the
okay. Yeah, you don't have the quality. You just have that it's big.
And we'll see why that is later.
Okay.
It's some crazy stuff going on.
All right. Thanks.
Yeah. Okay. And also, very briefly, I wanted to say for the Rips complex, we have a result which doesn't depend on the ambient dimension. It does depend on our thing being a subset of Euclidean space, which is we can show that the one-dimensional Rips persistent homology dimension is bounded above by the box dimension. And this is a corollary of a result which I don't think is in the literature anywhere, but proved that if we have a finite subset of Euclidean space, then we have a linear number of intervals. Okay. So going a little slower than I anticipated, so let's speed up a little bit. So I just wanted to say that to prove these upper and lower bounds for the persistent homology dimension, our strategy is to reduce it to extremal problems concerning the number of persistent homology intervals of a finite point set in Euclidean space. Actually, these extremal problems can make sense for finite subsets of general metric spaces, but here we're going to restrict attention to Euclidean space. So for the lower bound, we have one extremal problem, which asks for the largest subset of this, I guess, cube in the Euclidean lattice that has no stable persistent homology class in some very strong inclusion based sense. I'll say more about that later. So, okay, for the lower bound, we're looking for subsets of Euclidean space that don't have persistent homology. And for the upper bound, we want to ask, the first question is, how many persistent homology intervals can endpoints in Rm have? And that bound works for some cases and not others. And then with a little more work, we can reduce it to a question of how many long intervals can a well-separated point set in Euclidean space have? So hopefully I'll have some time to say stuff about that later. Okay, so the idea is we're going to try to prove this. We're going to reduce questions about this persistent homology dimension to extremal questions about the persistent homology. And I'll very quickly talk about the upper box dimension. So the upper box dimension has several equivalent definitions. One is we let n delta of x be the maximal number of disjoint balls centered at points of x. And we look at how this scales as delta goes to 0. So here's the dimension. So we take the limit supremum as delta goes to 0 of the log of n delta of x over negative log of delta. That takes some time to get used to. So what we're going to do is we're going to look at it instead as alternatively we could define the box dimension if it exists is the unique real number alpha, so that this quantity n delta of x, the maximal number of disjoint balls centered at points of x, so that it grows more slowly than 1 over delta to the alpha plus epsilon as delta goes to 0, but grows more quickly than 1 over delta to the alpha minus epsilon for all epsilon greater than 0. So it's basically picking out the asymptotics of n delta of x as delta goes to 0. So for the special case of a self-similar fractal, we get that n delta of x, I guess we should have a constant out front, is some constant times delta to the negative alpha, where alpha is the self-similarity dimension. So in this case, the box dimension picks out the scaling alpha. So, and just to say that the Hausdorff dimension is another fractal dimension, the box dimension, it agrees with the box dimension in many cases, and we, in general, have this inequality. Okay, and I just wanted to say that n delta of x can be replaced by other equivalent quantities. For example, the number of cubes in the grid of mesh delta that intersect x for a subset of Euclidean space. This gives an equivalent definition. We're going to be using this version of the definition for the lower bound and the one in terms of disjoint balls for the upper bound. Okay. Okay. Pause for a second. Any questions? Okay. So let's work. So what's the, we're going to reduce the lower bound. Oh, hold on. I'll just skip the examples. Okay. Lower bound. So recall the definition is we're looking for this cutoff. So above the cutoff, the beta weights of our persistent homology of subsets of our set are all uniformly bounded. And below the cutoff, we can find subsets of X where the beta weight is arbitrarily high. So just to review the definition. And we want to find a lower bound for this in terms of the box dimension. We want to write that find hypotheses under which the I-dimensional persistent homology dimension is greater than or equal to the upper box dimension. Okay? And the idea of how to prove this lower bound is, well, we're using the form of the box dimension where n delta of x is the number of cubes in the grid of mesh delta that x intersects. And the idea is if x intersects enough cubes, we can find some pointed set in x whose persistent homology is non-trivial. That's the basic idea. And so yeah, if the box dimension's high enough, we intersect enough cubes, we can find one point in each cube. That point set will give us some persistent homology, and we can bootstrap that to get some scaling relation between the persistent homology and the box dimension. So, okay, so how are we going to do that? So first of all, with the box dimension, we just know the boxes our set intersects. We don't know that we get the center of the box. In all likelihood, we don't have the center of the box. So if we're going to try to get a point in each box, we need our persistent homology classes to be stable in some sense. So here's the definition of stable that I'm using. So first of all, for a point in the integer lattice, we associate to it the Voronoi cell, so we get a cube. So here we're looking at the dots as our points in the integer lattice, and we associate to them their Voronoi cell, the cube around them. And then we say that a subset of the integer lattice has a stable persistent homology class if any point collection with exactly one point in each of the boxes gives us a persistent homology class, and of size that's bounded greater than 0, by some constant c greater than 0. So for example, in this figure here, we have these points have a stable pH1 class. If we take epsilon neighborhoods, if we grow balls around these points, we will get a pH1 class. And in fact, if we perturb the points anywhere in the box, we will get a pH1 class of size bounded away from 0. So here we can just move the points around. It doesn't change the fact that we get a pH1 class. So that's what I mean by stable. And then to give a better idea of what this means, let's look at an example of something that isn't stable. So here we have this 3 points. If these form an acute triangle, so if we take balls around them, we will get a pH1 class. We expand the balls around them, we'll have a little hole forming in the middle, and then it will disappear. But if we can move the points around in the cube so we don't get a pH1 class. Here we've moved the points in, they're still in the same cube, but this is an obtuse triangle, and we don't get a pH1 class. So these 3 points, this subset of the integer lattice, this has a pH1 class, but it's not stable. Okay? So then here's the idea. If we look at this brac of n, so this is the integers 1 of n, and then we look at brac n to the m, so this is a big cube living inside our integer lattice. So we look at this big cube in the integer lattice, and we want psi I m of n to be the largest subset of this big cube in the integer lattice that doesn't, so no subset of it has a stable persistent homology class of size greater than some fixed constant. Here we're just going to choose 1. So just to reiterate, psi I m of big N is the largest size of the largest subset of this cube in the integer lattice with our linear dimension big N, so that no subset of it has a stable phi class of size greater than 1. Now, why is this of interest? It's because our persistent homology dimension is defined in terms of all subsets of a given set X. So here this relates to all subsets of the cubes that X intersects. And then our proposition relating this extremal quantity to the dimension is that if we have that psi I m of n as an order of n to the gamma for some real number gamma, and we have a bounded subset of Rm whose box dimension exceeds gamma, then its first dimensional persistent homology dimension is greater than or equal to the box dimension. Now I have some slides on a sketch of a proof of why this works. I'm running a little low on time. 20 minutes left or 10 minutes?
Yeah, you have, say, 15 minutes and then time.
Okay, so I'm just going to skip the argument so we can get to the other extremal question. Or maybe I'll say a couple words because the other question's a little more straightforward. Okay, so the idea is that if psi I m of big N says something about the largest subset of a big cube in the integer lattice that has no stable persistent homology class in this inclusion closed manner. And that if this is in order of big N to the gamma, and we have a subset of Euclidean space with box dimension greater than gamma, then we get this lower bound for the persistent homology. Oh, this should be phi rather than ph1 for the I-dimensional persistent homology dimension in terms of the box dimension. Okay, so the proof idea is we take our subset here, it's a union of a cube and the Sierpinski triangle, and we let Bn be the set of cubes in the grid of mesh 1 over n. So we okay. Our thing has diameter 1. Oh yeah, no, that's fine. have mesh 1 over n that intersect x. So here the gray cubes all intersect our set, so we get all but one of them. And then the idea is subdivide. So we consider bkn for a carefully chosen k. You have to be careful about this. That's why I'm not doing the whole proof here, is it involves a lot of choosing the right k, choosing the right n. So here we have subdivided each of our cubes into grid mesh 1 over n, and we get a bunch of smaller cubes. So here inside of each gray cube, we get a certain number of purple cubes that correspond to a smaller mesh. And then the idea is that if k and n are chosen carefully, some of the cubes of Bn will contain enough cubes of Bkn to guarantee a stable persistent homology class of size 1 over n. That's the idea. We use this psi I n thing, this gadget, which says something about what is the, if we're bigger than this, then we must have a subset that has a stable class. So if k and n are chosen carefully enough, some of the cubes in Bn will contain enough of subdivided cubes to be greater than this cutoff. And then we can find a subset of them that will always give a persistent homology class of some size bounded away from 0. So here we have some examples of cubes. If we take any point in these cubes which intersect our set X, we get persistent PH1 class. That's the idea. And then we bootstrap this with k and n, take the limit as n goes to infinity. We do have to do some paring down. We just divide. Here we'll, I guess, cut off the one in the middle, so just to make sure we don't get any interference, and that gives us enough persistent homology to prove the desired results. So I'm just going to skip that proof. Okay, so then we have the results that if psi I m of big N is in order of big N to the gamma, then any subset of R m whose upper box dimension exceeds gamma has the phi dimension exceeding the box dimension. So then this raises the question, extremal geometry, extremal combinatorics, is what is the largest gamma so that psi I m of big N is order of big N to the gamma. And so far, this is quite a difficult problem to approach. But so far, I used an argument using triangles to show psi 1m is in order of big N to the m minus 1/2. So this is where the m minus 1/2 comes in. This is an argument having to deal with, it's quite a tedious argument, dealing with circumradii of triangles in the integer lattice. Hopefully there's a more elegant way to do this in higher dimensions, because the computations get quite complicated. So in particular, this implies that if x is a subset of Rm, then with box dimension greater than m minus 1/2, then dim pH1 of x is greater than or equal to dim box of x. And I just wanted to say the corresponding for the Rips complex is also interesting. Like this non-triviality question for subsets of the integer lattice for the Rips complex is also interesting. And I've made no progress on any cases for the Rips complex, like I have for the pH1 of in the Czech complex. So I hope people will get interested in these extremal questions. Okay, so let's see. Maybe I have 5 minutes to talk about the upper bound?
Definitely, yep.
Okay, so just to review the definition again, the I-dimensional persistent homology dimension is this cutoff, so that below the cutoff we can find subsets with arbitrarily high beta weight for the persistent homology. Above the cutoff, they're all uniformly bounded. Okay, so the upper bound, the first simple way to get an upper bound is we let, here we're talking about the number of intervals. So if we let psi I m of n be the maximum number of persistent homology intervals of a set of n points in the unit ball in Rm. And then the idea is if psi I m of n is in order of n to the c, and x is a bounded subset of Rm, then dim phi of x is less than or equal to c times the box dimension. Okay, so just to reiterate, psi m of n is the maximal number of I-dimensional persistent homology intervals of a set of endpoints in the unit ball in Rm. And as I mentioned before, if we have a finite point set, the persistent homology of that point set is the same as the persistent homology of the alpha complex. And the alpha complex is a filtration on the Delaunay triangulation. So we can use bounds on the number of simplices of the Delaunay triangulation to get a bound on psi I, the number of bars. So here you can go down for a specific I, you get specific bounds, but here you get order n to the floor n plus 1 over 2. That's the maximum. That's the number of simplices in the Delaunay triangulation. And in particular, taking m equals 2 implies the upper bound in our main theorem, which is that we get the number of simplices in the Delaunay triangulation of a subset of the plane is linear in the number of points. And this gives us that the first dimensional persistent homology dimension is less than or equal to the box dimension.
And Ben, do you also need to control the sizes of things somehow?
That's a good point. So this, basically, by controlling by the size, we get better estimates. Here we just need, so the idea of the proof, I guess I don't have time to go into it. The idea of the proof is we take a bounded subset of Rm. Using the box dimension, we can approximate it with a point set whose Hausdorff distance. So, okay, X is a bounded metric space, and if alpha is greater than the box dimension, then we can approximate it, any subset of it, with a point set with specific bounds on the size of the point set. So we find a point set within a finite point set that's within distance epsilon of that subset of X. That's the idea. First step is we approximate Y with a finite point set, and then we count the number of intervals of Y. So Y is going to give us, and then we have our interval counting lemma, which says that first we define phi epsilon of X to be all intervals of length greater than epsilon. So this answers your question. We're talking about intervals of size of the intervals of length greater than epsilon. And then the idea is if we approximate our Y, or we approximate X with Y, and the Hausdorff distance of X and Y is less than epsilon, then every interval of length greater than epsilon of X corresponds to an interval of Y.
I see, and then you just need to count the maximal possible intervals in Y.
Yeah. So then the idea is here. The idea is that what? We approximate Y with a finite. Okay, if X is a subset of Y, we approximate Y with a finite point set using the point approximation lemma, and we have specific bounds on the number of points we need to that, and that number of points is related to the box dimension. And with that, we can bound the number of long bars of the persistent homology of Y using this interval counting lemma. And then we can do a summation argument and get that it's uniformly bounded for everything for beta greater than C alpha, where C is the exponent in the number about controlling the number of intervals. That's the basic idea. I don't have time to go into detail.
Very cool. Yeah.
So this is in terms of the total number of bars of a finite point set. But in this, I was asking around, is this linear? I didn't know. Is for the check complex, could we have a subset of Euclidean space that has more than a linear number of bars? And Herbert Edelsbrunner suggested this example where we have two opposing arcs from unit circles in R3, and it appears that even well-spaced point sets have a more than linear number of bars. But all these bars are very, very small. So we don't end up with, at least computationally, it doesn't seem like this gives a counterexample to the conjecture that, that the persistent homology is less than or equal to the box dimension, i.e. that you don't have a set whose topology appears to scale in a way greater than the fractal dimension. And then we can observe, so this is an example where that previous argument, just in terms of the number of bars, that is not enough. But we can go back to the proof, which I didn't have time to do, and see when we approximated y with a finite point set, we only used that point set to count intervals of a certain length. So we can obtain a stronger result by controlling the number of phi intervals of a well-separated point set in Euclidean space rather than just the total number of intervals. That's the idea. I don't have time to go into it that much, but the basic idea is we let CIM be an exponent so that the number of persistent homology bars, length greater than epsilon, of a point set where all the pairwise distances are greater than 2 epsilon, we want to control that quantity. So before we were looking at the total number of intervals, and we wanted that to be less than or equal to some power law, right? We wanted to look at the exponent of that. So here, the point here is just we can look at the how the bounds for the number of long persistent homology bars of a well-separated point set and also get an upper bound. And I'm not going to go into the details of that, but I just wanted to point out. So if we do that, we also get an upper bound. And I want to point out this result of Cohen-Steiner, Edelsbrunner, et al. When they were studying Lipschitz stability, LP stability of persistent homologies. They ended up studying the alpha weights independently, and their results pretty immediately imply that the persistent homology dimension is less than or equal to the ambient dimension. So I just wanted to point out this argument with long bars allows you to prove this result. Okay. And then the question is, does this, I guess I haven't spent that much time on what CIM is. CIM controls how many long persistent homology bars of a well-separated point set can have. We've seen that the number of total bars of a well-separated point set can grow more than linearly, but if we control for how far the points apart, how many bars are longer than the separation between the points. If we can, that's a question is, does this equal 1? Can we only have a linear number of long bars for a well-separated point set in Euclidean space? I'd like to know that. And if we have that, then we get the desired upper bound, which is that the phi dimension is less than or equal to the box dimension. And I just wanted to say this is related to some questions of approximating Delaunay triangulations. So the reason our first bound doesn't work is the Delaunay triangulation could be more than linear number of simplices. So there's a question that's very important in computational geometry about, can you approximate the Delaunay triangulation with a linear size triangulation? And I wanted to say this homotopy interleaving distance, if we can, the question is, this is related to the question of, can we approximate the Delaunay triangulation with a linear size triangulation in the sense of this homotopy interleaving distance? I don't want to spend too much time on that, so let me just go to my conclusion. So we've taken the first steps towards answering the main question. So recall the main question is, are there hypotheses on a subset of Euclidean space under which the phi dimension equals the box dimension? And we answered this for a subset of R2. Recall that if the box dimension exceeds 1.5, we get that it equals the pH1 dimension. Took a lot of work using extremal combinatorics. I'm hoping that this work can be generalized to other cases, that we can control how the complexity of the topology in terms of the box dimension. And I just wanted to point out that probabilistic versions are also of interest. Now, the lower bound I think will be more difficult, and we don't get any help there. We don't get any help of going to the probabilistic case, because the extremal case is if we have trouble finding enough intervals for the extremal case, we're going to have the same trouble for the probabilistic case. But I wanted to point out actually the study of these alpha weights for persistent homology, even for subsets of Euclidean spaces of interest, and generalizes well-known questions about probabilistic questions about minimal spanning trees in Euclidean space. And I'm interested in working on generalizations of that. So my preprint's on the archive. The title of the paper is the same as the title of the talk. And please let me know if you're interested. And thank you for your attention.
Thank you very much, Ben. If you're in the audience and can unmute yourself, go ahead and unmute yourself, and let's thank Ben. So what questions do we have for our speaker? I have a couple, Ben. So first, just a technical question.
Yeah.
In your definition, you were looking at finite subsets,
Yeah.
and you says that the definition is really unchanged if you use infinite subsets. You said this is by stability. Is that relying on having bounded metric spaces?
Yeah, this is all bounded. I mean, like, if you're not bounded, then your box counting really isn't defined either. You can't really talk about unbounded things. I mean, the result of equality is that they both equal infinity because n delta of x is what? The maximal number of disjoint follow-centered points of your space.
I see.
So basically for any of this to make sense, you need to be bounded.
Okay, so next I asked a question about, you had an example of a check complex construction for a metric space.
Oh, Rips complex.
Oh yeah, you had an example of a Rips complex construction where the box counting dimension of that metric space was 1, but the Rips dimension was 2.
Yes.
And I asked, is there a check complex version of that? Let me chat here a web page. I think every Rips complex can be viewed as a check complex in some strange ambient metric space.
Okay.
So you'll have to. I don't know if you saw that link that I chatted, and if you didn't get it,
I'm still looking at my own screen, so I'm sure I can pull that up and see.
But you'll have to fact check that. But check that out, and that might.
But yeah, that makes sense, and I would not be surprised if that's by that.
And then the last question I had was, you cited this LP stable persistence result by I think Moleko and others.
Yeah.
Now, Now that's for like persistent homology of sublevel sets of
metrics.
And that's for persistent homology of sublevel sets of functions, right? Is there a version of that for simplicial complexes like Rips complexes and check complexes?
Well, so for check complexes, we're talking about the distance function to a finite point set.
I see.
I'm not sure for Rips complexes.
I see. Got it. Okay, but I see. Because the check complex is just the sublevel sets of the distance to the finite point set, you can use that stability here.
So actually, you can, I guess, with that framework, is like you can define a pH dimension of a function, not just a subset.
Sure. But when you apply that paper, when you talk about that paper, you're using the function, which is the distance to the finite point set, whose sublevel sets are just the unions of balls, i.e. the check complex. Is that right?
Yeah, and actually they do talk about like this cutoff of where it infinite or not for a given set and for all functions. So they do talk about this dimensional concept just briefly in their paper. But they were able to, with that, they showed this this less than or equal to the ambient dimension, which is not something I've done myself.
Sorry, which paper are you talking about?
The stability.
Oh.
The Lipschitz stability.
Oh. They show that what is less than or equal to the ambient dimension?
I guess basically what they show is that the PHI dimension. Because they're looking at, they want to control these sums of, they want to have some control over the sums of the lengths of the persistent homology intervals to a power. So then they can apply the Wasserstein distance. Like it's in their proof of the stability of the Wasserstein distance.
In order to apply Wasserstein distance or talk about Wasserstein distance, they need finiteness of something.
Yeah.
Oh, interesting. Okay. I will definitely have to go back and. Any other questions for Ben? Thank you very much.